Hello. In the previous lecture, we discussed the concept of mapping, we discussed the concept of sets, blocks, words, and how they are divided in the cache. We discussed the concept of temporal locality and spatial locality, and how that is the reason behind the usage of the concept of cache memory. And then we discussed that there are three types of mapping, that is direct mapping, n-way set associative mapping, and fully associative mapping, and that the distinction between the three is based on the number of sets and the number of blocks in each set. So that where we left the last lecture, and in this lecture let's start with direct mapping. Okay. So, like we discussed in the last lecture, in direct mapping, S equal to B. That is total number of blocks equal to total number of set, and that is each set will have only one block of memory. Right. So now let's right away dive into the concept. And one more thing, in our examples, the cache we are using will be having only 8 words. Okay, 2 power 3. So ours is a 8 word cache, and our main memory is a 2 power 30 word main memory. Why it is usually the main memory is for a 32-bit MIPS processor, it is 2 to the power 32 bytes, right? But here we are using what are we using? We are using word addressing, not byte addressing. Therefore only 2 power 30 words are able to be stored. Okay. So from the figure you can note something from the color coding, that certain blocks in the main memory are being put into certain specific blocks in the cache memory, right? And how does this happen? If you look at it, sets are 0 to 7, that is 0 0 0 to 1 1 1, right? 8 sets are there in the cache memory, and we have a binary notation for each one. So if you look at here, this is the address. Even though here we are using word addressing, the address given here is the byte address, right? So if you look at here, the last 2 bits are always 0, because it is word each word is given, right, and 4 byte jump is there. So let's forget about this. The next 3 bits are where the change is happening, right? Next 3 bits, that is given in blue here. So what we are doing is we are considering the set number and these 3 bits, the bits given in blue, not the last 2 bits, but the next 3 bits. So here if you see, these 3 bits are 1 0 0, and we are putting it here. What is the set number? 4, and what is the combination? 1 0 0. And here again, for 1 0 0 we are putting it into set 1 0 0. Similarly for this also, similarly for every block. So what is happening? We are taking these 3 bits, that is the 3 LSB after the last 2 bits, and we are taking that words or that blocks, and we are putting it into the set which is corresponding having that particular number. Right, simple. Since there is only one block per set in this particular mapping, in this particular example, or even in direct mapping, there is only one block per set, right? So at any given time, each set can only handle one block. So if you are taking this particular block and putting it here, and after a while if you want to take this block, or if the processor wants to access this block, then you will have to remove this block from the cache memory, and you will have to put this one here. Similarly for every set. Okay, let's see an example. To what cache set in figure 8.5? This is figure 8.5. Okay. To what cache set in figure 8.5 does the word at address 0x14 map? Name another address that maps to the same set. Okay. So first of all, what do we have to do? We have to convert this this into binary format. Then only we will know the bit pattern, right? So when we convert this, then the last 5 bits of this one will be 10100, right? It will be something 0000 something 10100. That means here we are interested in this part 101, and 101 means 101 is coming here. So that particular block will be, or that particular word will be stored into this set. Okay, that is how mapping is done. So other words that is having this is 0x34, 0x54, 0x74, 0x4, because all of these, if you have a look at it, will be ending with 10100. That is the thing that we are looking for. Okay, now these 3 bits that we considered here, right, which matches the set number and the last 3 bits of the word addressed, or 3 bits before the last 2 bits in the byte addressed main memory, those are called set bits, and it helps the processor or the digital logic circuitry to identify which set a particular which set in the cache a particular block in the main memory has to be moved when it is being taken, right? Then in the main memory, in the byte or word address, there are what is it called, 27, right? Out of the 30 we are using 3 as set bits in this particular example. Then there will be 27 remaining bits before that, 27 MSB. They are called the tag bits, right? They are called the tag bits. Why are they called? Okay, why are they called tag bits? Because for any bit combination, this last 3 bits, these 3 bits will be the set bits, and they will be denoting, okay, this thing is being copied into this particular set. But any of the 2 power 30 words having these last 3 bits as this can be copied here. So we don't know which of these 2 power 30 words are being stored into this block. To identify that, we use the other 27 bits of the main address. So that tag bits will also be stored along with the cache memory, along with this set, so that we know, okay, this particular set is having a tag this much, so that is corresponding to a particular main memory, right? So this is how a memory address, main memory 32-bit address is divided into. Like I said, there will be a 3-bit set bits. There will be a, this is for our particular example, okay, this is for our particular example of a 32-bit physical address and a 8-word cache memory. Okay, there will be 27-bit tag, and these two, the last two, the which the 2 bits we ignored when we were considering our word addressing, these are called byte offset, because within each word there are 4 bytes, right? So this is used to identify which what is the location of a particular byte within a block. But as far as within a word, not a block, within a word. But as far as we are concerned, this is of not much significance. When it comes to this direct mapping, the main takeaway should be that the contents of a main memory address location is put into a cache set depending on the set bits of the physical address, and the identification is done using, that is whether which address, which is the actual physical address of this data, that is identified using the tag bits. Okay, let's see a question. Find the number of set and tag bits for a direct mapped cache with 1024, that is 2 power 10 sets, right, and a one word block size. The address size is 32 bits. So here we are considering a larger cache, right, and it has 1024, that is 2 to the power of 10 sets, and one word per block, and each block is having only one word. Okay, and since it is a direct mapping, how many blocks will be there in a set? Only one. So let's see, cache is having 2 to the power of 10, therefore it will require 10 set bits, right? Log 2 log of 2 to the power of 10 to the base 2, that is 10 set bits are required, and the last 2 bits which are used for byte offset, that we are not using as tag bits, right? So 32 is the total number of bits in the physical address, that minus 10 bits used for the set bits, then 2 bits for the byte offset. So 32 minus 10 minus 2 is 20 bits will be there for the tag. Here in this example we were using 27 bits. So depending on the cache size and number of sets in the cache, the number of tag bits and set bits will change, but byte offset will be the same because the word size is fixed, right? It is a 4 byte word. Okay, now coming back to our actual example, that is 8 set cache memory. So this is how we check whether a data is actually there or not. Here we can see one extra term, right? There is one extra term V. This is called as a valid bit, valid. This denotes, if this is 1, it means that okay, the data in this particular set is valid, that is it has been copied from the main memory for use, and that it is not some junk value, because when the processor starts up there could be some junk value in the cache memory, and we don't know whether that value is actually useful or it has been copied from the main memory or it is being used or not. So to denote that this is the actual value and it is useful, we use something called as a valid bit V. Then we have the tag, right? Here we have a 27 bit tag. Then we have 8 sets and we use the 3 bits to identify the set. So these bits, the valid bit and the tag bit, are appended to the data. So this is how actually we check whether or we retrieve data. So we first of all we check, okay, fine, we check if we want to check if a certain memory, the data in a certain memory location is in the cache. First we find the 3 set bits or n number of set bits depending on the case, depending on the number of sets. For example, in the previous example we saw, it was 10 set bits. So there was 2 to the power of 10 sets. So it depends. So here we use the 3 set bits and find our specific set. Okay. Then what do? We need to know whether this data in this particular address is being stored here or not, right? So then what do? We check this tag bits. We compare these tag bits. This is a comparator, equality comparator. We check whether this 27 bits equal to the 27 bits of this particular data, this set. If it is the same, then fine, okay. It means the content here from this memory location is being stored in this particular set. But is it enough? No. Then we need to know whether that particular location data is valid or not, right? For that we again AND it with the valid bit of that particular set. Then if all these are true, that is if the tag of the set that we point to and the tag of the memory location are the same, there is an equality, and the valid bit of that tag is 1, then we get a hit. Only then we get a hit, and then if you want, we can access the data. Right. This is how for our particular example we check whether that data is correct or not, or we access that data. Okay, now let's see another example. How this here earlier we were just going through we were just assuming, okay, some data is coming from somewhere and all, but now let's see how this cache is used when we are running a program. Okay, we have a program here, something. So if we look at it here, whenever we are considering cache, we are dealing with memory access, right? Other things, other branching and things like that, we are not concerned. When we are considering cache, we need data access. That means we are considering whether, okay, some sort of memory read or write, memory access is required or not. So in this program, if you see, there are three lines of code which has memory access, that is 3 load words, others don't, and the addresses for this load word is 0x4 plus 0. This is a 0 register, right? Anyway, the value will be 0. So this is, they have done this, given this for simplicity. So the locations in the main memory that we need to take data from are 0x4, 0xc and 0x8. So what is your question? Okay, using the 8 entry cache of figure 8.7, that is the one we saw earlier, show the contents of the cache after executing the following loop code. Assume that the cache is initially empty. What is the miss rate? Okay, so this loop will go on for how many times? It will go on for 5 loops, right? Because we are initially loading the T0 register with 5. Then we are using a branch equivalent to 0. We are comparing T0 to 0. Then only it will be done. Otherwise, it will keep on looping, right? So, it will access for 5 times. So let's see what will be the condition. So if you look at it, these are our sets, right? And 0x4 means 0000 something 00100, that is the actual physical address. So many zeros will be there in the front, and the last 5 bits will be 00100. So the set bits are for 4 the set bits are 001, and it will be stored in set 1, right? And for this one 0x8, then it will be similar, using similar logic. What will it be? It will be 0100. Sorry, 01000, 1 followed by 3 zeros. So it will be stored in set 2, right? And for C, it will be 0110. So it will be stored in set 3, that is 011. So if you look at here, for each loop the processor is accessing the data from these 3 locations, right? 0x4, 0xc and 0x8. The thing is that once it has been copied into the cache, then the processor doesn't have to go back to the main memory. It is already there in the cache. So the processor will keep on updating this data or taking this data. There is nothing else to be done. It doesn't have to go back to the memory, right? So and the thing is that all of these 3 are stored in different sets. So there is no conflict between this. There is no need to rewrite any of these values, right? So what happens in the first loop? This memory, the data in this memory location is not there in the cache. We don't know if it is there or not. So we will assume it is not there. So it has to be taken. So in the first loop, this is a miss. This is a cache miss. Again, this is a cache miss. Again, this is a cache miss. So in the first loop we have 3 misses. What happens in the second loop onwards? The second loop, when the processor try to access it, okay, this is already there in the cache, so it is a hit. So again it is a hit. This is also a hit. So this continues for the next 4 loops, right? So if you look at it, there is a total of 15 memory accesses, right? 3 access per loop and 5 loops, so 15 memory accesses, and out of that 3 misses are there, that is in the first loop, and 12 hits are there, that is in the later 4 loops. So what is the miss rate? 3 by 15 equal to 20%. This is the miss rate, and this is the final configuration, or the how the cache will look. There is no conflict here, so there is no issue. There is no need to remove some value and put another data into that. Okay. Now let's say another question. What is the miss rate when the following loop is executed in the 8-word direct mapped cache from figure 8.7? Assume the cache is initially empty. Right. This is our another thing. So let's see how many, what are the memory access operations coming here. Only 2 are there, right? Load word and another load word. And the memory locations to be accessed are 0x4 and 0x24. And there are 5 loops. So 2 loops, 2 memory reads, memory access per loop, and 5 loops. And a total of 10 access will be there. So to find the find the miss rate, we have to see how many how many misses are there out of 10. Okay, so if you look at it, 0x24 and 0x24, when you convert them into binary and when you take the set bits, you will come to know that both of them map to set 1. That is 0x4 will be mapped to set 1 and 0x24 will be mapped to set 1. Okay, so initially what happens? 4 is loaded into set 1. Then in the next instruction, 24 has to be loaded into set 1, right? So what happens? The 4 is evicted and 24 is put into that cache, that set. So here this is a miss, this is also a miss, because it is not there, initial 24 is not there. In the next loop what happens? The processor looks for 4, but 4 is not there, 24 is there in set 1. So again this is a miss. So 24 is evicted and 4 is put there. Again same thing happens here, 24 is not there, so 4 is evicted and 24 is put there. This keeps on going for the complete, this keeps on going for all 5 loops. So here what is, it is a miss in every case. Therefore the miss rate is 100%. It is a 100% miss rate. So this is a problem with, this is one of the major problems with direct mapping. That is, since there is only one block per set, and if there is, when another block of having the same set bits comes, there is an issue. For solving this issue, we go for an n-way set associative mapping. That is, there will be n blocks per set. So we will be stopping this lecture here, and the next lecture we will see an n-way set associative mapping. Thank you.